Okay, in these slides we are going to study a couple of examples about what we have already studied about Kirchhoff voltage law, Kirchhoff current law, series resistance, parallel resistance. So we start with example 1. In example 1, we have an electromagnetic force generator with 12 volts connected to this combination of resistors. R1 is 20 ohm, R2 is 20 ohms too, R3 is 30 ohms, and R4 is 8 ohms. Since it has not mentioned what is the internal resistance of the electromagnetic force generator or the battery, so we will assume the internal resistance of the EMF device is 0. Okay. Now the question is, what is the current through the battery? So it is required to find out the current passing through the battery in this case. At the beginning, let us arrange this combination of resistors. If we look about resistance R2 and R3, we can find out terminal 1 of R2 is connected to terminal 1 of R3, and terminal 2 of R2 is connected to terminal 2 of R3. So electrically, R2 and R3 are parallel resistors, even though they are not physically parallel, but electrically they have two connected nodes, B and C. And the potential difference between the terminals of R2 is the same as the potential difference between the terminals of R3. That's why R2 and R3 are in parallel. So effectively, the first step here is to get the equivalent resistance of R2 parallel to R3 in a single equivalent resistance. Let us call it R23, for example. So we replace R2 and R3 by a single equivalent resistance R23. Then it will be a single loop composed of R1 and R23 and R4. And in this case, these three resistances are connected in series. So by getting the potential differences on this closed loop, we can obtain the current in this loop, and actually this current is the current inside the EMF device or the battery. So this is our plan. As we say, R2 is parallel to R3, so we can replace R2 and R3 by their equivalent parallel resistors. And we said that if we have two parallel resistors, the equivalent resistance would be the multiplication of the two resistors over the summation of the two resistors. So the equivalent resistance R23 would be R2 multiplied by R3 over R2 plus R3. And actually R2 is 20 ohms, R3 is 30 ohms. So 20 ohms multiplied by 30 over 50, 20 plus 30. So it would be 12 ohms. So this is the equivalent resistance for these two parallel resistors R2 and R3. Now we have a single loop circuit. We will apply Kirchhoff voltage law, and assuming that the current loop is moving clockwise, so the electric field would be in the same direction of the loop. So electromagnetic force E would be positive, and the voltage drop at resistance 1 would be negative. The voltage drop at resistance 2, 3 would be negative. The voltage drop at resistance 4 would be negative. So the summation of the potential differences in this loop would be E minus I1 multiplied by R1 minus I1 multiplied by R23 minus I1 multiplied by I4 equals 0. R1 is 20 ohm, R23 we have calculated 12 ohms, and R4 is 8 ohms. Okay, so the only unknown in this case is the current in this loop. So we can solve for this current. It would be E over R1 plus R23 plus R4, R1 20 plus 12, 32 plus 8, 40. So I1 would be 12 volts over 40 ohms is 0.3 amperes. And actually, this I1 is the current that passes through the battery, which is the required current. Okay? So the required or the unknown current is I1 is 0.3 ampere. Now we have the current which passes through this loop. So we can find out the potential difference at each resistor. So the potential difference at resistance 1 would be I1 multiplied by R1. And the potential difference at the combination between R2 and 3 would be I1 multiplied by R23, which is in this case is 0.3 ampere multiplied by 12 ohms, so it is 3.6 volt. So the voltage difference between the point B and C is 3.6 volts, and the voltage difference on R4 is I1 multiplied by R4. It would be here 2.4 volts. Okay, so once we have obtained the current in the loop, we can obtain the potential difference at each resistor. So let us keep in our minds now the potential difference between the point B and C is 3.6. We will use it in the other section of this book. Okay. The second part of this problem, it is required to find I2 through the resistance R2. Effectively, in this equivalent circuit, we don't have R2. We have combined the resistance 2 with the resistance 3 in parallel in an equivalent resistance R2. But let us remember the original circuit was like this, R2 and this R3. So it is required to find out the current I2 through the resistance R2. In this case, actually I2 is a part of I1 because I1 enters the node B, is divided between the two passes I3 and I2. So the question is, what is the value of I2? To find out the current I2, we have to find out the potential difference between the point B and C, which we have already calculated, V23, the voltage between B and C, 3.6 volt, over the resistance R2. R2 is 20 ohms. So in this case, the potential difference between the points B and C, which is V23 is the potential difference between point B and C, equals the current I1 multiplied by R23. We have calculated this 3.6 volt, and then we say that I2 is the potential V23 or VBC over R2. So this would be 3.6 volts over 20 ohms. It is 0.18 amperes. And since I1 equals I2 plus I3 by using Kirchhoff current law, because the current enter the node B equals the currents leaving the node B, so we can say that I3 equals I1 minus I2. So if we are interested in finding out I3, we can obtain by using I2 and I1, which has already obtained. So I3 is I1 minus I2 is 0.3 amperes minus 0.18 amperes. So it is 0.12 or 0.12 amperes. Okay. Another example. Here we have multi-loop circuit, and we have three EMF devices, E1, E2, and E3. We have a combination of resistors R1, R1, R2, R1, R1, and it is required to find out the currents I1, I2, and I3. What's the value of I1, I2, and I3? Assuming that E1 is 3 volts, E2 is 6 volts, and here this E2 also, so this is another 6 volts, and R1, 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 R1 is 2 ohms, R2 is 4 ohms. First of all, let us agree on that if we have taken the node A as a junction, so the currents enter this junction I1 plus I2 should equal the current leaving this junction I3. So I3 equals I1 plus I2. If we apply the same theory on the junction B, we can say that the current enter junction B equal the currents which leaves the junction B, so I3 equal I1 plus I2, which is the same. So if we take node A or node B, we will have this equation. So this is a relation between I1, I2, and I3. Now we need to have other two relations such that we have three relations or three equations in three unknowns, I1, I2, and I3. So if we start with the left loop, and assuming that we are going clockwise, and we start from point B. So first of all, we will have a voltage drop at resistance R1. The voltage drop at resistance R1 is minus I1 R1. Then we have electromagnetic force in the same direction of the loop, so plus E1. Then we have voltage drop in resistance R1, so we have minus I1 R1. Then we have voltage drop in R2, so it will be minus I3 multiplied by R2. And actually, we know that I3 equals I1 plus I2, so we can replace I3 by I1 plus I2. Okay? Then finally, we have a potential difference opposite to the direction of the loop, E2, so it would be minus E2. Then we have reached to the starting point B, so equals 0. So this is the left loop. We applied Kirchhoff voltage law at the left loop, starting from point B to reach once again to point B. Numerically, if we apply this with the values, here minus I1 multiplied by R1 minus I1 multiplied by R1. So this is I1 multiplied by 2 multiplied by 2. Here minus I1 multiplied by R2, which is 4 ohms. So here we are talking about I1 multiplied by 8 ohms and I2 multiplied by 4 ohms, and we replace this in the other side. So these are in positive, and we remain this in the same side. So E1 3 volts minus E2 6 volts. So 3 minus 6 would be minus 3 volts. So numerically, this is the first equation. Okay. Now we go to the right hand loop, and we will start from where this I2 R1. So we will start from point A. Okay, we will start from point A, and we are going in clockwise direction. So from A through the resistance R1. No. Sorry. I'm going from point B once again. Sorry. I'm going from the point B toward point B. And in this case, I am going counterclockwise. So I'm going I2 multiplied by R1 will introduce a voltage drop minus I2 multiplied by R1, because the current is in the same direction of the loop, which is counterclockwise. Then I have the potential of the electromagnetic force device E2 in the same direction of the loop, which is counterclockwise. So E2 is taken in positive. Then there is a voltage drop across resistance R1, so it would be minus I2 multiplied by R1. Then there is a voltage drop across R2 equals I3 multiplied by R2, and I3 is I1 plus I2, so this minus I1 plus I2 multiplied by R2. Finally, the voltage of the EMF force E2, which is in opposite direction of the loop, so it is minus E2. Then we have returned back to B. Once again, I start from B to R1 minus I to R1. Then we have the potential E2 in the same direction of the loop. Then the potential difference at R1, which is minus I2 multiplied by R1. Then the potential difference I3 multiplied by R2. Then minus the potential E. This is the second equation for the second loop. Now by arranging this stuff, we can say that we will take the currents in the other side, so it will be in positive, and here I1 is multiplied by R2 only, so it is I1 multiplied by 4 ohms only, and I2 is multiplied by R2, R1, so it is I2 multiplied by R2 plus R1 plus R1, so 4 plus 2 plus 2, so I2 multiplied by 8. This equals what? Equals E2 minus E2. E2 minus E2 would be 0, regardless what the value of E2. So 6 minus 6 equals 0. Now we have two equations, two unknowns. If I1 plus 4I2 equals minus 3, and 4I1 plus 8I2 equals 0, we solve these two equations simultaneously. We can obtain I1 equal minus 0.5 amperes and I2 is 0.25 ampere. We should note that the result of I1 is negative. This means that I assume that I1 is going in this direction, but the actual current is going in the opposite direction. So I1 is actually going from A to B, not from B to A. So the value of I1 is 0.5, and the direction of I1 is from A to B, not from B to A, as I have assumed. But for I2, the value of the current is 0.25 ampere, and the direction is actually in the original direction that I have assumed. So regardless what we have assumed, the calculations will obtain if this direction is correct or not. Alright? Finally, to find out I3 would be I1 plus I2. I1 plus I2 by summation, it would be minus 0.5 ampere plus 0.25 ampere would be minus 0.25 ampere. Once again, I3 is negative. It means that the value of I3 is 0.25, but the direction of I3 in the opposite direction to the direction that I have assumed. Okay? So, thus, as a last step, we correct the answer by reversing the arrow I1 and I3, making the arrow in this direction and this arrow in this direction and I3 in this direction. And in this case, I1 would be 0.5 ampere, I3 is 0.25 ampere, and I2 is 0.25. Okay?